Asslamoalikum. Welcome to the course of Artificial Intelligence. In today's lecture video, we will discuss the topic of game theory. We will also discuss essential algorithms such as Minimax and alpha-beta pruning. For extra material, please refer to chapter number 5 of the Artificial Intelligence, a Modern Approach book by Russell and Norwich. This is the agenda of today's lecture. Game theory is very interesting topic. Have you ever wondered how computer is able to defeat you in two-player games? For example, like chess, tic-tac-toe, checker, poker, solitaire, etc. This phenomena of computer being able to play multiplayer games is known as game theory. All games have rules. We all know that. If you are well aware of the rules, then the board is yours. You are winner of the game. Same is the criteria for computer. If those game rules were built into the system, only then the computer could win. To achieve this, one has to develop an algorithm that takes into account the number of players and the rules, hence the invention of game theory. In simple words, programming game rules into system is game theory. We define game theory as choosing from a set of rational choices in a multi-agent situation. By rational choices, it is meant calculated choices, choices that are based on reasoning and proper logic. In game theory, we deal with deciding on given set of options, which means that you can select from many possible moves at a given time. Choosing correct move is purely based on reasoning and calculation by the algorithm. An important thing to notice here is the phrase multi-agent situation. It means that there are more than one agents in the environment and they affect each other's success. Von Neumann is credited for invention of game theory. In Python, Easy AI library is used for development of two-player games. Game theory works in multi-agent environment. We already know that multi-agent environments are of two types, comparative and competitive. Lecture number 4 has clear descriptions of these two types. Please see that lecture if you need more discussion on this topic. When environment is multi-agent and is competitive, then such environment gives rise to adversarial problems, also known as games. As move of one player affects the move of other, thus planning in advance is required. This planning in advance, the unpredictability of these other agents can introduce contingencies into agents' problem-solving process, which means you cannot clearly predict next move of your opponent while playing games. Thus, logical reasoning and calculation is required. This logical reasoning is programmed into machine, which makes it able to play adversarial games. We have already discussed the topic of multi-agent environments in which each agent needs to consider action of other agents and how they affect its own welfare. Moves that agent have to take next are planned in advance. Every agent considers the move taken by its adversary or opponent and then plans its own moves in advance before taking actual action. This creates an interweaved web of moves in the form of graph. Whenever there is graph, there is possibility of search. Thus, game theory is game playing algorithm that uses search. In adversarial search, we examine the problems that arise when we try to plan ahead in a world where other agents are planning against us. Thus, we will be working in multi-agent environment. Let's play. Let's discuss the concept of game theory through an example of simple game that we all know, tic-tac-toe. Tic-tac-toe is a 9x9 grid two-player game in which you have to mark the boxes with selected sign, and the one who gets the same sign marked diagonally, horizontally or vertically wins the game. These are the rules of the games. We all must have played this game sometime or another in our life. Thus, rules of the game are readily understandable by us. Now suppose you are playing game against computer opponent. Your sign is cross and opponent's or adversary's sign is O. Game begins and first turn is yours. You mark a random box with X. It's now adversary's turn, which is computer. It will mark a box with 0. You will try to mark X in a box that can help you win. And computer will try to mark O in a box to stop you from winning. This is typical human psyche. Whenever we play, we try to defeat opponent by reducing their chances to win. Just like in Ludo, we never let opponent's token roam free if we can kill it. In other words, you are trying to maximize your utility or benefit by taking effective moves. The opponent or adversary is trying to minimize your utility or benefit by reducing your chances to win. This war of maximizing and minimizing the benefit is given the name of game theory. In the same way, complete game will be played by marking O's and X's. If game theory has been correctly programmed into your machine, the machine will never let you win. Either you will lose or it will be a draw, as in the situation of this example. Since the beginning of modern AI age, game theory has been part of it. Programs like chess, checkers, etc. have been developed and are now in very advanced form. Deep Blue was a chess-playing computer developed by IBM. It is known for being the first computer chess playing system to win both a chess game and a chess match against a reigning world champion Garry Kasparov. It is well understood by now that we can control only moves of our player. We cannot control moves of opponent or adversary against which we are playing game. Contingency means unpredictability. The planning in advance of other agents can introduce unpredictabilities or contingencies into the agent's problem solving process, which means you cannot clearly predict next move of your agent while playing games. Thus, logical reasoning and calculating is required. This logical reasoning is programmed into machine, which makes it able to play adversarial games. It must be kept in mind that we are playing against adversary that is rational. Proper game rules and player details have been built in the programming of the opponent agent. Thus, moves taken by our adversary are properly calculated, are logical, and it always tries to win, which means it tries to maximize its own utility by minimizing ours. Now let's see how are two-player games different from search, or how are games different from search problems. Let's discuss search first. We are well aware of the phenomena of search. In search, we do not have any adversary or opponent. Well, it is cleared. Solution is method for finding goal. We are looking for goal. We are always looking for a path that leads us to the optimal goal. We have evaluation function in search, which is estimate of cost from start to goal through given nodes. Now let's focus on game theory. In games, we have opponent or adversary against whom we have to play. This is the first difference. When there are multi-agent environments, then there is unpredictability. Unpredictability of opponent means deciding what move to take, as presence of other player introduces a kind of uncertainty. In games, we often have time limits. These time limits force us to take an approximate solution. Evaluation function in game theory is utility or goodness of player position, which means that different moves have different utilities attached to them. The higher the player is closer to success, the higher will be its utility and vice versa. These are the examples of different games. We already know that problem formulation is the first and foremost step in solving any problem. We have already formalized problems when we were studying search. Problem formulation is necessary as it states details relevant to problem before actually jumping into problem solving. If problem is formally stated and formalized, then programming solution for that problem becomes very easy. Now let's discuss problem formulation for game searches. Like every other problem formulation, we start by defining start state of the game or initial state. For example, when we started playing tic-tac-toe, initially the grid was empty. Thus, the initial state of tic-tac-toe is empty. In chess, the initial board is empty. Thus, initial state will be empty for chess. Second step in problem formulation is to define detail about the players of the games. We provide details like how many players are involved in the gameplay. Is it 2-player game or 4-player game like Ludo? We also specify which player will take first move, etc. In third step, we decide actions which are actually legal or correct moves that player can take. By legal, it is meant that moves taken by agent must be according to rules of the game. What can be goal of any gameplay? Goal is actually the final termination point and final ending point of game. In scenario of games, it is always game over state. There can be 3 states of game over, either win, lose or draw. Search objective states why we perform search. In game, we perform search to find what sequence of moves the player will take to win, or in other words, what sequence of moves will maximize its goodness measure, that is, utility. As opponents' moves are unpredictable, thus we also perform search in game theory to consider the possible moves of the opponent as well. Let's discuss this graph. This graph shows sequence of possible moves that a player can take from current position for tic-tac-toe game. Tic-tac-toe is deterministic. It is deterministic as next move can be decided from current move. It is a two-player game, thus its environment is multi-agent. Each player has to take turns to win the game. First, it is turn of player 1, then player 2, thus it is a turn-wise game. To solve game problems, such graphs are drawn in which every possible move that a player can take from current position is stated. For example, initially, when the game starts, the tic-tac-toe 9x9 grid is empty. This shows the initial position of the game. When player 1 takes turn, he can mark X in any of the possible 9 cells as shown by successors of initial states. There are 9 successors of initial state. These are all possible 9 positions that X can take. Thus, initial state is expanded into 9 successors. These are actually all possible moves that player 1 can take while taking his turn. He can mark X in first cell, he can mark X in second cell, in third cell. It all depends on his choice. Next turn is taken by player 2. This is the area where player 2 will take turn. All possible moves that player 2 can take from current position are stated. For example, if X is marked in the first cell by player 1, then at what position 0 or O can be marked by player 2. Those all possible positions are stated as shown in the graph. Same goes for all rest of the 8 possible moves. Due to shortage of space, those 8 possible moves have not been shown in the diagram. Each move that is taken by player 1 is further expanded into 8 possibilities by player 2, thus expanding the game search by many folds. In the same way, the graph keeps expanding, taking into account the last moves. It can be seen that the next move taken by a player is dependent on the last move taken by previous player. In the same way, the graph keeps expanding by taking into account the last moves. It can be seen that the next move taken by player is dependent on the last move taken by previous player. This is what makes it deterministic. As we discussed before, the game ends when we lose, win, or it's a draw. This defines the terminal states. These are the terminal states. Here, losing situation is marked with the utility of -1. Draw situation is marked with the utility of 0 and win situation is marked with the utility of +1. The player should always strive to maximize his utility to achieve win, which is +1. The player 2 always tries to minimize the utility of player 1, thus it goes for -1 situation. We will discuss how to deal with the contingency problem now. Previously, we saw that all possible moves were expanded and some utility function was there to define winning, losing, and draw situation. We haven't yet described how to select moves from all possible sets of moves. Minimax algorithm is used to select best sequence of moves. This is the first, foremost, and simplest algorithm to implement game theory in computer sciences. Minimax algorithm solves the problem of contingency or unpredictability. Without use of Minimax algorithm, we are not sure which move is best to be taken and which will lead to win for us. It tells us what moves are best that we can take to win the game. Utility function defines the best move. The higher the utility function for a move is, the best that move is. It is one of the oldest algorithms in AI and is generally used for two-player games. It gives very good results for deterministic games. It always starts from max position. Then min and max each take turn to repeat until terminal state is reached. For example, in given figure, the game ends after 2 turns. This is the initial point. The root node is always at max. Then the turn is of min. These are the terminal utilities that have been provided. Let's discuss the rules. As Minimax algorithm is generally of two players, thus one player is assigned max and other is assigned min. Max chooses that move which have maximum utility from set of all possible moves. Min chooses that move which has minimum utility from set of all possible moves. We already know that tree data structure is used to show map of all possible moves. Each level is designated alternatively to both players. If level 1 is player 1, then at level 2 it will be player 2 and so on. At each level, we make decision based on criteria of either min or max, whichever is assigned to the player. Last level has terminal utilities. It has been already discussed. Minimax algorithm is bottom-up approach. We start from bottom and take terminal utilities to upper levels by choosing maximum and minimum on turns by players until problem is solved. Our goal is to reach the top of the tree from bottom. Thus, this is a bottom-up approach. Let's begin the game. Let's solve Minimax algorithm through a worked example. Terminal utilities are given at last level, which tells us the terminal or game over utilities of the game. When example starts, we only have terminal utilities. We will start by marking all levels of tree with max and min alternatively, starting from root node which is always at max. Minimax algorithm is bottom-up approach. This means that utilities from bottom are taken upwards. In this example, we start from level 3, which is min. This means that now turn is of player 2 and task of player 2 is to minimize utility function. Thus, we will choose minimum values from leaf nodes and pass it to parent node. As two successors of this parent node are 10 and positive infinity, of which 10 is the smaller, we have to choose minimum value of these two. We will choose 10 and pass it on to its parent node. In the same way, we will go on choosing minimum values for all of these. For example, this node has no other successor, thus 5 will be passed as it is, as 5 is the minimum value for it. This node has no other successor, thus minus 10 will get passed to the upper node. And this node has two successors, 7 and 5, out of which 5 is minimum, thus 5 gets passed upward to the parent node. This node has only one successor, which is negative infinity, thus it will, as it is, get passed to the parent node. And out of these two, the smaller one will be passed, the minimum one will be passed, which is minus 7. We will choose minimum values from the utility function. Now that we have chosen minimum values, we will move one level up, which is of max. At max level, we will choose maximum values from all the successors. For example, this node has two successors, 10 and 5. Out of these two, we will choose maximum. As 10 is maximum, 10 will get passed to the parent node. Minus 10 is the only successor of this node, thus minus 10 will get passed as it is. This node has two successors, 5 and minus infinity. Out of these two, we have to choose maximum as we are in this max level. Thus 5 will get passed, and 7 is the only successor of this node, thus minus 7 will get passed to the parent node. Then again we have to choose minimum out of these two. Minus 10 will get passed, and out of these two, minus 7 will get passed. These levels will show which value we have to choose, either min or max. These are actually turns taken by the players. Root node is always at max level. So out of these two, which one is maximum? Of course, minus 7 is maximum, and it will get passed to the root node, defining the path that would be taken by the player to win the game. This path would be taken by the player to win the game. The path that shows the minus 7 utility. This is example problem. This is to be solved by you. It is added for your own practice. This is a pretty simple algorithm. Minimax algorithm explores the complete tree before deciding the best possible path, thus making its complexity exponential, which is big O of maximum branching factor raised to maximum depth of the tree. When larger games are solved using the algorithm, it takes much time and space to provide the solution as it visits each and every node and keeps each and every node in the memory. it becomes impossible to handle larger problem using Minimax algorithm. Alpha-beta pruning is a variant of Minimax algorithm. It is updated and improved form of Minimax algorithm. In alpha-beta pruning, we prune or cut off those branches that are useless, or in other words, that would never be played by the rational player. Alpha-beta pruning reduces complexity of simple Minimax algorithm and is a much faster alternative. In alpha-beta pruning, tree to be searched becomes shorter and concise version of tree that we use for searching in Minimax algorithm. Thus, searching shorter tree requires much less time and space. Solution is found much faster. Let's discuss technicalities of alpha-beta pruning. Just like Minimax algorithm, here also we start by mentioning max and min against all levels starting from root node. After mentioning max and min, we now take two additional values as alpha and beta. Alpha is always initialized with negative infinity and is always set as max. Beta is associated to minimum level and is always initialized with positive infinity. We will change the value of alpha when we are at level max, and we will change the value of beta when we are at level minimum. After we have initialized value of alpha and beta, we will follow depth first search for searching the path to take by considering this condition of greater or equal to b. This condition is very important and is the defining criteria of tree pruning. Concept of depth first search is at core of alpha beta pruning. If you do not have grasp on depth first search, you are advised to see lecture number 10, link to which will be provided in description as well as in I button. Now let's understand this concept through worked example. Let's suppose this is the tree that needs to be searched using alpha beta pruning. Like Minimax algorithm, we will firstly start by marking all levels by min and max, alternatively starting from root to n. Root level is always marked max. From this image, gray areas are max areas, which mean maximum value will be selected in this area, and green areas are in min area, which means minimum value will be selected from its successors. After levels have been marked, now we set initial alpha and beta values for all the nodes, leaving terminal nodes as their utility is already set. Remember, initially all nodes have an alpha and beta, which is initially minus infinity and positive infinity respectively. One more concept to remember here is that at min level we will change the value of beta, and at max level we will change the value of alpha. This must be kept in mind as we move forwards. As already mentioned, that this algorithm follows depth first search. Thus, we will directly go to the depth of the tree, and leftmost node, which is leaf node, will have the control. This leaf node 3 has the control right now. As parent is at min level, thus we will select minimum value from successor of parent node, and value of beta will be changed as beta is associated with minimum value. As we do not have data of second successor yet, thus we will assign value of 3 to beta. Notice that we haven't actually assigned any node value yet to this parent node. We will assign this value once we have checked all of its successors. Now we will perform condition check. Before exploring the right successor child of every parent node, this condition check must be performed. Here parent node is this node, and before exploring its right child, this condition check must be performed. We will check if value of alpha is greater or equal to beta. Here value of beta is 3 and alpha is negative infinity, which makes the condition false, as negative infinity can never be greater or equal to 3. Thus the condition is false. As condition is not satisfied, thus we will explore the right child of this parent node. As this is min level and task of beta is to choose the minimum of these two, and right child of parent node is 4, which is greater than 3, this value of beta will remain the same. It will remain unchanged, and node value of 3 will also be set to 3, and 3 will become the final node value. Following depth first search, we will move to the parent of node 3, which is this node. and it is at max level. As at max level, we have to select maximum value and alpha is associated with maximum, and we do not have right child of this node yet. Thus, for time being, 3 is as it is assigned to alpha. Notice value of beta has not changed. As at max level, only alpha is to be selected. Value of beta gets changed only when we are at min level. Now that again by following depth first search, we will have to move right, and we know that before exploring right child of any node, we have to check for a special condition of alpha greater or equal to beta. We will check now. Is 3 greater or equal to infinity? Of course, 3 is smaller than positive infinity. Thus, condition becomes false and permission is granted to explore right child of this parent node. Now following DFS, next node to be searched will be leaf node 2. The DFS algo will directly take us to leaf node 2 following root left right regime. Notice value of alpha is passed as it is to its child node. In alpha beta pruning, if parent has gained value of either alpha or beta, it is passed down as it is to its children nodes. This is another important concept to be kept in mind for alpha beta pruning. As this node is at min level, this value of beta will be changed only as beta is associated with minimum level. Beta will be assigned 2 as we have not explored the value of right child yet. As we already know, before exploring right child of any parent node, we have to perform a condition check. When condition check is performed on this particular node, it is found that condition becomes true as alpha, which is 3, is greater than beta, which is 2. When condition becomes true, we do not explore the right child of that parent node. Thus, this branch that leads to 1 is pruned. The idea of pruning is that in one level above, we have already got better value, which is 3. At this min level here, beta says that I will only accept value which is less than 2. Even if beta becomes minus infinity, it wouldn't have any effect on one level above. As at next level, we have to choose maximum of these two nodes, and we have already chosen a better value. It will only choose value of this node if it was greater than 3. Thus, if alpha is not greater than beta, and this condition becomes false, only then we explore right child in anticipation of finding better maximum value of alpha. Node value will be now finalized as 2 and maximum value will be selected as 3 out of these two. Depth first search takes us back to this node here. As level suggests, we have to choose minimum value and thus beta is assigned 3 for now. Condition check is performed again before exploring right child and condition becomes false as negative infinity is not greater than 3. DFS will take us to the deepest tree level to the node 7 again. Value of beta obtained at parent will be passed down as discussed before. This is the generation line of beta. Beta gets passed down its generation line. From this level, we have to select minimum. We have to work on this level. This value of beta will be changed as we are at minimum level, but as it can be seen that passed down value of beta is already smaller than the value which utility function is giving us for now. This beta will remain the same. The value of beta will remain unchanged. Condition check will be performed, and as condition is false, of course, negative infinity is not greater than equal to 3. Thus, we will explore the right child. But value of beta still remain 3 as 3 is smaller than 8. Node value will be set to 3 and we will move one level above the tree. Our control will be here now. At this level, we have to choose maximum value. As yet, we do not have data of right side of the tree. Directly 3 will be assigned to alpha. Again, condition check will be performed and condition will become true as alpha is equal to beta. This right side of the tree will be pruned. This complete portion in Eclipse will be pruned and node value will be set at 3. Now following DFS, control will move here, one level above from the previous level. we have to choose minimum. Thus 3 will be set as node value, minimum of these two, and we already have minimum, thus node value will be set at 3. Now control will move towards the root node of the tree. We already know that root node of the tree is always at max level. This value of alpha is to be assigned. As we do not have that of right side yet, thus 3 will be assigned for now to alpha. Value of alpha will be changed from minus infinity to 3. Following DFS will take us to node 2 here directly. Value of alpha obtained from root node will be passed down as it is down the generation line. We are currently at minimum level. Thus value of beta will be changed and 2 will be assigned to beta. Condition check will be performed, and as condition becomes true, thus right child will be pruned. 2 will be assigned as node value, and we will move upwards to the next level here. Here at this level we have to choose maximum value as this level suggests. Thus value of alpha will be changed as alpha is associated with maximum, but notice that we will not assign 2 to alpha as alpha already has a greater number 3. We will not assign this 2 to this alpha as alpha already has greater value. Again condition check will be performed as 3 is less than infinity. Thus condition is not satisfied, and we will explore the right side of the tree. DFS will directly take us to the deepest node, which is 1. We have to choose minimum from here. Thus value of beta will be changed. Beta will be assigned 1. Condition check will be performed as current value of alpha which was passed down is greater than value of beta, which is 1. Thus condition is satisfied, and this branch will be pruned. Remember that this 3 is being passed along the generation line from root node. Node that currently has the control is this node, and we have to choose the value of beta. As we do not have information or data of the right side or right successors of this node, thus beta will be assigned 3. Condition check will be performed here as well. We have assigned beta 3. Condition check will be performed, and of course a is greater and equal to 3. The condition here is being satisfied. Thus this whole part of the tree here is pruned. We cut off these all branches. This complete part of tree is being pruned as this condition here is becoming true, which means that we do not have to explore this area. In this, search is reduced, which saves time and space, thus resulting in lesser complexity. Path that the search will take is through node 3 as suggested by root node. The algorithm tells us that I will have maximum chance of winning game if I took this path, which is through node 3. That gives me the utility of 3. This is practice example for you. This is your homework. You have to solve it by hand. Remember, following the rules and the criteria as per the worked example. This slide discusses the functions that can be used when programming alpha beta pruning in code. Maxv function is called for max nodes, and alpha is updated if needed. If we already have greater value of alpha, then it doesn't need updating, as we have seen in previous worked example. We write minv function or minimum v function to find minimum values, which updates value of beta if required. If we already have minimum value of beta, then beta is not changed. Condition check is performed in both functions, and both check for pruning in case condition is satisfied. Each of these functions test for appropriate pruning case by checking the condition. Let's discuss properties of alpha beta pruning. It must be kept in mind that if pruning is performed, it does not affect the final results. It means that if same tree was searched using Minimax algorithm and alpha beta pruning, then both will provide the same final path. Alpha beta pruning provides the same result as Minimax, but with lesser time and space complexity. When unwanted parts of tree are cut off, then obviously effectiveness will be improved. Our search will never get stuck in useless areas that might never lead to successive gameplay. It reduces time complexity by 2. Its bigger notation is maximum branching factor raised to maximum depth of the tree divided by 2. It is exponential, but it is 2 times lesser. This ends the lecture for today. Allah Hafiz.